Good morning, everyone. So welcome to the first session of the day. And we're going to start with Eugenia Colafranceschi, who is a postdoctoral fellow at Western University. And she's going to talk about type 1 von Neumann algebras from gravitational path integrals, Ryu Tagayanaki as entropy without holography. So Eugenia, you can start whenever you want. Thanks.
Okay, thank you. Thank you very much to the organizers for the opportunity to present this conference. It is not on?
Okay.
Now? Yes? Yeah. Okay. Okay. So, so the main idea behind this work is the one that we can actually make progress in quantum gravity by exchanging ideas between different communities and comparing views, comparing different views on the same physical problems. So a way to work across different approaches is follow the same logic. So we start from some very general assumptions and we ask what follows from them. Now, actually today I'm going to follow the inverse logic, meaning I want to start from a result in a specific approach and then ask which assumptions are needed, which requirements are needed in order to obtain that result. And in particular, which approaches satisfy them. We have many candidates: loop quantum gravity, string theory, group field theory, and so on. And in particular, what I'm going to focus today is entropy in quantum gravity, and more specifically on the so-called Ryu-Takayanagi formula. The Ryu-Takayanagi formula was originally proposed to compute holographic entanglement entropy in ADS-CFT, but I'm going to show that this can actually be understood more generally. So the Ryu-Takayanagi formula in ADS-CFT was proposed to compute the entanglement entropy of a certain region R on the boundary, and it was given in terms of the area of a surface in the bulk. Now, the question I'm addressing today is, can we understand this formula without holography, so purely from the bulk? And back to the original point, in particular, which assumptions are required to get this formula without holography? And I'm going to argue today that the answer is positive. We can indeed understand Ryu-Takayanagi even without holography. So let me say something more about the Ryu-Takayanagi formula. So it was originally proposed to compute holographic entanglement in anti-de Sitter spacetime, as I said, but the present understanding is much more general. And indeed, as shown by Lekovics and Maldacena in 2013, this formula can be understood, can be derived by generalizing the Gibbons-Hawking method to compute the entropy of a black hole. So the idea of Gibbons-Hawking was to interpret the path integral on the Euclidean black hole as a thermodynamic partition function and then derive the entropy via standard thermodynamic arguments. And since the non-trivial part of this variation is concentrated near the horizon, what we get is a contribution from the area of the horizon itself. Lekovics and Maldacena generalized this technique to the case in which, to any case in which you have a path integral prescription for the construction of a state. And in particular, they did that by using the replica trick, in which you consider n copies of the system and you compute the trace of your density matrix to some power n. Then you analytically continue in the number of copies and you compute the entropy. And so again, since the non-trivial part of this variation is concentrated near a surface, which is the surface invariant under replica symmetry, just as the horizon, the black hole horizon is the surface invariant under the rotational symmetry of the black hole, you get this contribution from the area. So now, why you might be interested in the Ryuta-Kayanagi formula, let me give you an example. The Ryuta-Kayanagi formula is the first version of a much more general formula called the generalized entropy, in which you also get a contribution from the quantum field on the classical geometry. And this formula had a central role in some recent results about the information problem. It gives an entropy that follows the page curve. Is this the correct entropy of the Hawking radiation? This is very much debated and is not something I'm going to talk today, just to give you an idea of the role of this Ryuta-Kayanagi formula. So where to start? So we said, okay, we want to understand Ryuta-Kayanagi formula without holography, and we want to identify the general assumptions to do that. So where to start? Well, what we can ask, what we can expect from a theory of quantum gravity is that it contains a map from boundary conditions to complex numbers. So in particular, that given a set of boundary conditions, boundary metric, boundary values for matter fields, we get a number that can be interpreted as the transition amplitude associated to that process. Now, we might call this map the Euclidean gravitational path integral, and you might think of this map as a sum over geometries. However, this is not going to be a requirement in our work. This is just an intuition, if you like. But what we are going to do is to make some assumptions about this map, so to list some axioms for the gravitational path integral. So I said the Ryuta-Kayanagi formula is computing an entropy for the boundary, but let me be more precise what we are going to explore today. So consider a gravitational system with two asymptotic codimension two boundaries. So in a Lorentzian setting, you might think at a Cauchy surface whose boundary is disconnected. And the Hilbert space, so let me call these two boundaries left and right. The Hilbert space associated to them a priori does not factorize over left and right. And so in which sense can we talk about a reduced state just for the left or the right boundary? And in which sense can we associate an entropy to that? So in particular, to answer the question, can we understand this Ryuta-Kayanagi entropy as entropy without holography, we would like to construct a Hilbert space associated just to the left boundary, so that the Ryuta-Kayanagi formula can be understood in terms of a standard trace on this Hilbert space. What I'm going to show today is that we can actually find a structure of this type anytime the Euclidean path integral satisfies a simple set of axioms. Before proceeding, let me just mention some related work. So the first point I want to stress is that an axiomatic approach to quantum field theories and gravity is not new. Atiyah listed the axioms for topological quantum field theory, and these in turn inspired several attempts to define a gravitational partition function. Also, the Ryuta-Kayanagi formula has been explored beyond the ADS-EFT context, in particular for spin network states. And also, in particular in the holography community, there has been a lot of effort lately in understanding Ryuta-Kayanagi purely from the bulk point of view. I already mentioned Lekovicz-Maldacena, which is the first step of this story. Then more recently, Witten and colleagues show that the Ryuta-Kayanagi formula can be derived as an entropy of a type 2 von Neumann algebra. However, when we think the entropy for a standard quantum system, so an entropy in terms of a standard Hilbert space trace, which is just a sum over an orthonormal basis, and which is the trace that provides a state counting interpretation for the entropy, we are thinking of a type 1 trace. So a different way of rephrasing the goal for this work is that we want to derive the Ryuta-Kayanagi entropy as entropy of a type 1 von Neumann algebra in order to have a state counting interpretation for this entropy. So this is the plan. I'm going to list the axioms for the gravitational path integral. I'm going to construct a Hilbert space from it and an algebra of observables acting on this Hilbert space. Then I will show that these algebras are type 1 von Neumann factors, and finally I will show how to compute an entropy as an entropy of this algebra. So, as I said at the beginning, we are focusing on an Euclidean gravitational path integral. What is this path integral is a machine that takes some boundary conditions, and by M I'm referring to not just a choice of topology, but also a choice for the metric and values, boundary values of matter fields. And to this set of boundary conditions, which I will call source manifolds, to remind you that I'm including choices for metrics and matter fields, to this source manifold, the path integral associates a number which, as I said, you might want to think at as this sum over geometries. So when we cut a path integral along a surface, we can imagine this path integral to compute the inner product between two states, which are the states, if you want, prepared by the boundary conditions on the two sides of the surface. And in particular, in the case in which this surface is reflection symmetric, you might think of this path integral as computing an inner product, as computing the norm of the state, and so to give a non-negative number. So this was to give you an intuition of which kind of actions you might want to require for the gravitational path integral. In particular, we are going to require these 5 axioms. So the first one is just that this path integral is a well-defined map from a set of smooth boundary conditions to complex numbers. The second one is just is a real function of possibly complex boundary conditions, which means that if you consider your source manifold and you complex conjugate the sources, then also the path integral takes the complex conjugated value. We ask it to be reflection positive. This is for what I said, because we want ultimately, we want to interpret this path integral as defining an inner product. We require continuity as a very mild condition, which means that if your source boundary manifold contains a cylinder, then this map is continuous under a small deformation of this cylinder. And the last axiom is factorization, meaning that if you are computing the path integral for a boundary manifold which is disconnected, the path integral also factorizes over these boundaries. Okay, so now that we have the axioms, so we want to construct a Hilbert space. As I said, you can intuitively you can think that every time you cut a path integral, you are defining a Hilbert space on the cut. In particular, so let's consider a manifold, and following this logic, you can take the 2 halves of the manifold and associate states to them. And you want, in particular, the path integral computed on the 2 manifolds glued back together as computing an inner product between these 2 states. But there is a problem that if you start for all generic surfaces, associated to, and you associate to them a state, surfaces which have this codimension 2 boundary that I'm calling B, when you glue them back together, you might not find a smooth manifold. So to cure this problem, what we do is that we introduce rims. So we require that all these surfaces with a codimension 2 boundary contain an infinitesimal cylinder, which is just the B times some small interval, so that anytime we glue back together two such surfaces, the resulting boundary manifold is smooth, and so the path integral is well defined. I'm going to call Y the set of these codimension 1 surfaces with a B boundary, and in particular with the underline the set of linear combination of these source manifolds. So starting from this set of states, we have, thanks to this inner product defined by the path integral, we have a pre-Hilbert space, and then we can consider the quotient by the null space and complete the result in the standard sense, and in this way to get a well-defined Hilbert space. Now, this is just a sector of the full quantum gravity Hilbert space. In particular, is the sector associated to this codimension 2 boundaries. So again, in a Lorentzian setting, you might think of this as the set as the Hilbert space associated to a Cauchy surface with B boundary. Okay, so I listed the actions and I constructed the Hilbert space. Now I want to construct an algebra of operators from the path integral acting on this Hilbert space, because we ultimately want to understand the entropy as an entropy of this algebra. So let's consider now, instead of surfaces with one B boundary, surfaces with two disconnected B boundaries. So source manifolds, codimension 1 source manifolds with these two B boundaries. These surfaces will define states in the Hilbert space associated to this disjoint union of B boundaries, but they also define operators acting on this Hilbert space. And what we want to do next is to promote the set of linear combinations of these two boundary surfaces to an algebra. So to do that, we need to define a product on this set of surfaces. So in particular, we can define a left product in which you take two surfaces, let's say A and B, and you glue them together by gluing the right boundary of A to the left boundary of B. This is the left product, and the other way around defines a right product. Now, for convenience, anytime I will write the simple product AB, I'm referring to the left one, but so I will mostly refer to the left case, but everything is symmetric for the right case. So the set of surfaces, in particular the linear combination of these two boundary surfaces equipped with this left and right product define respectively a left and a right surface algebra. The two algebras, the left and the right one, are related by an antilinear isomorphism, which is given by complex conjugating the sources and swapping the left and the right labels. And we are going to see that these left and right surface algebras have a natural action on the left and right, respectively, B boundaries of the two boundary Hilbert space. Now, a crucial ingredient in this story is the trace, because, as I said, we are interested in computing an entropy. Well, the path integral defines naturally a trace on this algebra. You just take this two boundary surface, this boundary source manifold, and the trace of this element is just the path integral that you compute with the boundary manifold obtained by gluing together the two B boundaries. And you can easily see that this trace is cyclic because by gluing together the two manifolds, you get the same boundary manifold. And in particular, the trace, so defined on the left and the right surface algebra, corresponds to the inner product on the two boundary Hilbert space. And thanks to the axiom on the positivity of the inner product for reflection positive surfaces, we get that this trace is also positive definite. Okay, there is another ingredient which is very important for what follows, which is a trace inequality. So we have this algebra, we define a trace. This trace satisfies this inequality, saying that if you consider two elements, A star and B star, you have an upper bound by the trace of the A star A and B star B separately. How we prove this? Well, just to give you an idea, we start by considering surfaces in this set of two boundary surfaces, but we use them to define elements of a four-boundary Hilbert space. No? So in particular, you can consider A and B to define these states in the picture associated to a four-boundary Hilbert space. And then you can just use the Cauchy-Schwarz inequality to show that the norm of the inner product between these two states is bounded by the norm of the two states separately. So thanks to this, we have that the trace inequality holds, and this will allow us to get the crucial result in the end. So we can define, once we have these abstract algebras, the left and the right one, we can consider how they act on the Hilbert space. So we can in particular define a representation of the left surface algebra on the Hilbert space. So how this algebra acts is very naturally an action of an element A on a state B is just given by gluing the A surface to the B one, and so defining a new state which is just the product of A and B. And these operators, we can show that these operators are bounded thanks to the trace inequality I showed before. And we can similarly define a representation of the right surface algebra on this Hilbert space. Now, these operator algebras, the representation on the Hilbert space, get a trace just from the trace on the abstract algebra. So this is straightforward. Okay, so far we have defined not just the Hilbert space, but also an algebra of operators from the path integral acting on this Hilbert space. Now we want to study the structure of these algebras, because they will tell us about the structure of the Hilbert space. So far we have two commuting algebras of bounded operators on the Hilbert space. These are not yet von Neumann algebras, but we can take the closure in the weak or strong operator topology, or equivalently taking the double commutant of these algebras and define von Neumann algebras associated to the two boundaries. And we show that the trace defined on the operator algebras can be extended to all positive elements of the von Neumann algebra. So in particular, the way you can do this is to take an element A and to consider the inner product with two cylinder states or cylinder operator equivalently, and take the limit for the length of the cylinder that goes to 0. And in this way, we have a well-defined trace on the von Neumann algebra. Why this is important? Because not just for the definition of the entropy, but also because we can study the structure of these von Neumann algebras just by studying the trace. So in particular, we can prove that this trace is faithful, which means that is zero only if the element is zero, is normal, and this is, if you like, a way to show that there is a sense in which this trace is continuous, and is semi-finite, which basically means that not all elements have infinite trace. Also, this trace satisfies the trace inequality because we can use an extension of the four-boundary argument I showed before. And in particular, if we apply the trace inequality to a projection in the left algebra, we get that the trace of the projection is bounded below by 1. So these properties turn out to be enough to identify the structure of this von Neumann algebra. In fact, we can rely on some known results on von Neumann algebras. So the first one is that every von Neumann algebra is a direct sum of or an integral of factors which are algebras of trivial center. These factors can be type 1, 2, or 3. There is no faithful, normal, and semi-finite trace on type 3, and since we got these properties, it means that we cannot have type 3 factors. And on type 2, for any faithful, normal, and semi-finite trace, there are non-zero projections with arbitrary small trace. But we got a lower bound for the trace of a projection, which means that we cannot have type 1 factors. Type 2 factors, sorry. So we just get type 1. So these left and right surface von Neumann algebras must be a direct sum or integral of type 1 factors. And in particular, it's easy to show that the spectrum of the center of these algebras is discrete. And so this means that the algebra is actually a direct sum of type 1 factors. So now that we have the type 1 von Neumann algebras, we have these left and right algebras which are each other commutants on the Hilbert space. And so in particular, they must have the same center. And this means that both algebras have the same decomposition as on the same index set on type 1 factors. From the structure of this algebra, we can derive a structure for the Hilbert space because we can decompose this Hilbert space into eigenspaces of the center operator. So in particular, we will have that our two-boundary Hilbert space is a direct sum of Hilbert spaces for the two boundaries, and that in each sector the Hilbert space factorizes over the left and the right boundary. Okay, so far we constructed an Hilbert space and operator algebras just by requiring some actions for the path integral, and we show that these are type 1 von Neumann factors. So now we can define an entropy for that. So in particular, we know that faithful, normal, and semi-finite traces on type 1 are unique up to a normalization constant. This means that in a given sector of the algebra and of the Hilbert space, the path integral trace must be proportional to the standard trace on the Hilbert space. And we call the proportionality constant this n mu. So what can we say about this constant? So we can consider a one-dimensional projection for which the standard Hilbert space trace is equal to 1. We already know, thanks to the trace inequality, that we have a lower bound given by 1 on the trace of this projection. And this followed from the trace inequality, which in turn followed from the positivity of the inner product on the four-boundary Hilbert space. Well, we can actually generalize this argument for a Hilbert space with a generic n number of pairs of two boundaries. And by doing that, we can show that the constant is actually a positive integer. So what we get is that in every sector of the theory, the path integral trace is proportional to a standard trace on the Hilbert space, and the proportionality constant is actually a positive integer. This means that we can define an extended Hilbert space by introducing an additional Hilbert space with dimension set by this positive integer. And we are going to call this an hidden sector because it's not probed by the algebra we constructed. But thanks to extended Hilbert space, we have that the path integral trace is actually equal to a standard Hilbert space trace on this extended space. So the full extended Hilbert space is given again by a direct sum over these mu eigenvalues of two factors, one associated to the left, one associated to the right boundary. And in particular, the hidden sector in this way, thanks to this extended Hilbert space, we can interpret the path integral trace as a Hilbert space trace on this extended set. So the trace defines, the path integral trace naturally defines an entropy on the left and on the right boundary. How? So in particular, given a state, so a two boundary defined by a two boundary surface, we can define a reduced density operator associated just to the left boundary by tracing out the right part, which means just to glue together the two right boundaries. And the von Neumann entropy on this element of the algebra will just be given by the usual formula, so trace rho log rho with the path integral trace. But what happens now is that thanks to the relation between the path integral trace and the standard trace on an extended Hilbert space, this entropy actually has a state counting interpretation as a left entropy on this extended Hilbert space. And so we can compute this entropy via the replica trick, just following the Lekovitz-Maldacena construction. So in particular, we can consider the trace of this element, of n copies of this element, given by the path integral over the surface, which is just the gluing of these n surfaces together, and compute the von Neumann entropy by using the replica trick. And so just by applying the Lekovitz-Maldacena construction, we have that if the theory admits a semi-classical limit described by Einstein-Hilbert or JT gravity, then in such a limit this entropy is given by the Ryuta-Kayanagi formula. So in particular will be given by the area of a surface which is the surface, the fixed point under replica symmetry. Okay, so let me summarize what I show you today. So our main question was to understand if the Ryuta-Kayanagi formula proposed in the ADS-CFT context makes sense without holography, just from the point of view of an algebra of bulk observables. And the setting in particular is the one of having a Hilbert space associated to codimension two boundaries, disconnected, and we ask, can we associate an entropy just to the left or to the right boundary? And this point is not obvious because the Hilbert space a priori does not factorize. But what we showed is that anytime the gravitational path integral satisfies a simple set of actions, then this path integral defines a type 1 von Neumann algebra of observables associated to these codimension 2 surfaces. The path integral defines a trace, and so an entropy on these algebras. The Hilbert space on which the algebra decomposes, act decomposes into a direct sum of factors associated just to the left and to the right. And crucially, the path integral trace is equivalent to a standard trace on an extended Hilbert space. And this provides a state counting interpretation for the entropy even when the gravitational theory is not known to have an holographic dual theory. And in particular, in the semi-classical limit, this entropy is given by the Ryuta-Kayanagi formula. Okay, thank you very much for your attention.
Thanks, Eugenia, for the very nice talk. Any questions? So let's start here, and then Eugenia.
I have a couple of questions, but maybe let me ask both of them. The first question was, except in the very last part where you mentioned Ryuta-Kayanagi, for the rest of your talk, where was it important that this path integral was over approximately Einstein gravity? I mean, it seemed to be a very general framework where the action could be anything, but somehow we would think that, you know, all of these nice properties only appear when you're thinking of a nice theory where there's a local action which is approximately. So that's one question. And the second question is about the second last part that you had about the state counting interpretation. Is the claim that purely from gravity we would be able to count the microstates because you also had an explicit construction of the Hilbert space? So say we had the eternal black hole in ADS and we computed its entropy using the path integral. Are we saying this is giving us an explicit description of the microstates as constructed in the Hilbert space?
Okay, so regarding the first question, no, it's not important in any point that the theory admits an Einstein-Hilbert, that in the semi-classical limit is well described by the Einstein-Hilbert gravity, because as you said, we use that just at the very end, just when we say, okay, we constructed these algebras, then if you use the replica trick Slakovic-Maldacena did, we get an entropy. In the semi-classical limit, this entropy will be given by the Ryuta-Kayanagi formula. So that is the only part in which we are making some assumptions about the theory besides the list of axioms that we listed. So the axioms are very general and are not saying anything about the action of the theory or the particular realization of the path integral. The second question, so what this construction is saying is that there is an interpretation in terms of microstates, but it does not give any information on what these microstates are. Indeed, this interpretation, I mean, we get this interpretation on an extended Hilbert space, which contains a part that is not probed by the algebra we constructed. So in particular, we don't have an understanding of which kind of microstates are there. We just show that this interpretation in terms of microstates is possible, that the path integral knows in some sense that there is an interpretation in terms of, because we constructed this through the path integral trace, but these hidden sectors are there to signal our ignorance about these microstates at this stage.
Thank you, Eugenia, for this beautiful talk. So I also had two questions. You already answered the first. That's the one that Surat asked. So I go to my second question, that is, do you have a physical interpretation for this hidden sector that you need in the construction?
No, not really, because as I said, this is the part that the algebra actually cannot probe. So it's more a statement of like the degrees of freedom that are missing in the construction. So
okay, thank you.
We just have time for the last question here. Sorry, I know.
Yeah, I had a very simple question. Why do we require the algebra to be normal? You mentioned in on one of the slides, one of the conditions was that the algebra should be normal. And
The trace?
yeah. And then you said that, so, and that's why we have to use a type 1 algebra later on. Yeah, condition number 2. Sorry, the trace.
No, this is not an assumption. This is an outcome. The fact that the trace is normal so that you can prove.
Okay.
Yeah.
So in fact, we have time for one short question. So I think, okay, sorry, Hannah.
Yeah, so if I understand correctly, the construction does not depend on the topology of the bulk manifold. Should I understand this as it works for any given topology, or the path integral you have in mind includes a sum over topologies?
So the path integral we have in mind, indeed, I mean, so the intuition we get in particular comes from a sum over geometries and topologies for the path integral. So if you have a standard, just a fixed topology, then it's quite straightforward, in particular that the last axiom is satisfied. Because if you have a fixed topology for the bulk, I mean, the failure of this factorization can come from space-time wormholes between the two. So in particular, it arises when you consider indeed the sum over all possible topologies in the bulk. However, following the Marolf-Maxfield construction in which you show that this contribution from wormholes actually lead to a decomposition of your theory into sectors. In these sectors, the contribution from the wormholes is suppressed, and this axiom holds sector by sector. So if you have a sum over topologies, you have to be careful on how these possible funny topologies can contribute to the path integral, because this axiom is likely to fail. Let me also say that in the Lekovitz-Maldacena derivation, the sum over topologies is important because is what is the reason why you get a non-trivial contribution from this surface invariant under replica symmetry. So, yeah.
Okay, thanks. So I think we not have more time for questions. There are a couple of people that wanted to ask you questions, so hopefully they can find you at the break.
Yeah.
Thanks again, Eugenia.